It is my pleasure to introduce our next speaker, Nathan Wagner from the Department of Mathematical Sciences, George Mason University. The title of his talk you can see from the screen. Yes, please now. Nathan, you can.
Okay. Thank you very much, and thanks to both the organizers for putting together this very nice event and the opportunity to speak. So I'm going to talk today about optimal sparse bounds and commutator characterization without doubling. And this is based on joint work with Francesco D'Amelio, Aaron Lin, and Brett Vick. And the topic itself, the work that we've done is somewhat technical, so I'm going to try to put some things in a broader context because I know that there are people here that um, are interested in various subfields of harmonic analysis, and so some people might be more or less familiar with the topics here. So I'm going to try to put everything in context as best I can without getting too technical. Okay, so first, I'm going to talk about BMO. So that's a space of functions that probably many of you have seen before. If we think about just BMO on the real line, it's defined to be um, a space of functions that have bounded mean oscillation. So that means when we take the integral average of the absolute value of the function minus its integral average on that interval. So the bracket notation here refers to the integral average of B over I. That oscillation or that mean oscillation remains bounded over all intervals I. And so this is a space that's very important in analysis for a variety of reasons. One is in the context of Calderon-Zygmunt singular integral theory. So the prototypical example of such an operator is a Hilbert transform. These operators, by definition, are bounded on L2, but they also map LP to itself for P in the reflexive range strictly between 1 and infinity. However, these operators fail to be bounded on L infinity. So instead, they map L infinity to BMO, which is a bigger space. There are functions in BMO that are not bounded, though every bounded function belongs to BMO. And kind of the typical example of a function in BMO grows logarithmically. So functions in BMO can't grow very fast. They can't grow, for example, polynomially, but they can grow logarithmically. This space BMO is also important because it's sufficient for interpolation on the LP scale. So if you want to interpolate with an endpoint estimate and another endpoint estimate to get strong type estimates in the middle, the BMO estimate is enough to do that. The key property of BMO that's really going to be relevant for this talk is its utility in characterizing commutator norms. So there's this celebrated result that goes back to the 70s due to Koifman, Rockberg, and Weiss that the commutator of the Hilbert transform with multiplication by a measurable function b is bounded on LP if and only if B belongs to BMO. So the commutator here is measuring how much the operator H commutes with multiplication by another function. And uh, the amazing thing is not only is this a characterization, but we can also provide an equivalent norm on B. The BMO norm is equivalent to the operator norm from LP to LP of the commutator. And there's a similar result that holds for the Riesz transforms in higher dimensions. And finally, BMO is important because of duality. So Charles Pfefferman has a very, very, very famous result back to the 70s that the dual of the real Hardy space H1 is isomorphic to BMO. And real Hardy spaces are also important in the context of singular integrals, connections with complex function theory, and so forth. So this is a really fundamental, important space, and we want to understand it more. That's the underlying motivation of a lot of this talk. A variant of BMO called dyadic BMO arises when instead of taking the supremum over all real line intervals, we instead restrict to, say, dyadic intervals in a fixed dyadic grid. And this is sort of well motivated because the intersection of two dyadic BMO spaces associated to two well-chosen dyadic grids actually recovers the continuous BMO space. So there's a way to sort of pass from the dyadic to the continuous. There's also characterizations of dyadic BMO in terms of dyadic operators. So, a recent result due to Stephanie Pettermichael and collaborators says that the commutator of a well-chosen dyadic model of the Hilbert transform and multiplication by B is L2 bounded if and only if B belongs to dyadic BMO. This result was actually proved in the biparameter setting by Pettermichael. So the operator H is really a tensor product of H with itself because we're in the biparameter setting. But I don't believe this was actually written down in the literature, even in the one parameter setting before this paper came out. So the point is we can characterize dyadic BMO using dyadic operators, just like we characterize continuous BMO with the ordinary Hilbert transform. So we're going to talk about non-homogeneous harmonic analysis today, which means we're going to change the underlying measure. And so here everything is with respect to Lebesgue measure. All of these averages defining the BMO space are computed with respect to the Lebesgue measure on the line. But the theory actually doesn't change too much if you assume your measure mu is what's called dyadically doubling, which means that there exists some constant c bigger than zero so that the mu measure of the dyadic parent of I is at most c times the mu measure of I. So this I hat here refers to the dyadic parent of I, and that's the unique dyadic interval containing I with side length equal to twice I, the length of I. And if mu is dyadically doubling, this theory still works, and you can still get a characterization of BMO with respect to the measure mu. So basically, there everything is the integration is taken with respect to mu. This is 1 over a measure of mu here rather than the Lebesgue measure. This integral average is with respect to mu. And we also would define the dyadic model of the Hilbert transform appropriately. But if we do that, everything still works. So the main takeaway here is that you can still get a characterization of BMO, dyadic BMO, via a commutator norm if your measure is sort of nice enough and satisfies this dyadic regularity condition. But there's motivation to move beyond the doubling setting, so what we call in the harmonic analysis community the non-homogeneous setting. So here mu is not assumed to be a doubling measure. And historically, non-homogeneous harmonic analysis was developed with a lot of applications in mind, for example, to partial differential equations and geometric measure theory. So, for example, topics such as rectifiability and the Cauchy integral, where you look at the Cauchy integral on some very, very rough planar curve, for example. But this topic has developed intrinsic interest in its own right. And sorry, that's a typo there. It should be geometric measure theory, not geometric metric theory. So there was some really influential work done on this topic by Tulsa and Nazarov, Trail, and Wahlberg, and they developed really an extensive machinery to deal with continuous singular integral operators, for example. But the interesting thing is that this machinery does not extend to the corresponding dyadic model operators in the same way, and that's kind of a motivation in part, for this talk. Okay, so I'm just going to go over the kind of basic objects that we're going to be dealing with. So when we're in dimension 1 on the real line, we just take, for example, the standard dyadic grid. So intervals of the form 2 to the minus k m plus 1. And some additional notation, if we have a dyadic interval I, which is colored here in blue, the two dyadic children of I are denoted I minus and I plus, so those are the pink and green intervals respectively. The dyadic sibling of I is what's in orange here, and it's denoted by an IS. And the dyadic parent of I is denoted with I hat, and that's this gray interval sitting up top here. And one additional piece of notation, if we have a natural number k, dki denotes the collection of dyadic subintervals of I of length 2 to the minus ki. So these are sort of the descendants of an interval that are k levels down in the dyadic grid, right? That are obtained by subdividing into two k times, right? Um, so in the Lebesgue measure setting, we can take the collection of dyadic intervals and create a system of Haar functions, right? So this is known as a Haar function or a Haar wavelet, right? This sort of square wave here. And it's well known that the Haar wavelet system, if I index my Haar functions with respect to the dyadic intervals, forms an orthonormal basis for L2 of R, just with the Lebesgue measure. And we can, because of that, we can write F in terms of its orthonormal basis decomposition, right? And the Haar function is basically the indicator function on the left child of the interval minus the indicator function on the right child of the interval with an L2 normalizing constant out front, right? And actually, up to a choice of sign, this is the unique function that is constant on the children of I, supported on I, has L2 norm 1, and mean value 0. So those actually completely determine the values of the function up to a constant. Because you could multiply by -1 and it would just flip everything up to a sign. Yeah. Um, and we're concerned with operators that are kind of dyadic models of Calder-Sigma operators. And I'm going to explain that more in a second. Um, but we want to basically look at operators called Haar shifts, which map Haar functions to Haar functions. So if you look at the definition here, the Haar function hj, which is embedded a certain number of levels down in a ancestor interval I, is mapped to another Haar function supported on k, which is also a descendant of I, but at sort of a different dyadic level. So these Haar shifts sort of scramble the Haar functions around and move them between dyadic levels, but kind of do so in some sort of bounded way, depending on this complexity parameter uv. And such operators are always a priori bounded, for example, on L2, as long as they say have bounded constant coefficients. Okay. Um, the reason why people cared about these was because about 20 years ago, Stephanie Pettermeikle noticed that this operator, which I've denoted by a script P, which maps the Haar function hi to hi minus hi plus, so it's a Haar shift of complexity 0, 1, is a good model for the continuous Hilbert transform, which we all know is given by convolution of one with 1 over x. Really, this integral is interpreted as a principal value, of course. But this operator can be recovered in a pointwise sense via an averaging of these dyadic shifts over some probability space. And you should think of this probability space as it's basically parameterizing a collection of dyadic grids where we kind of shift the dyadic grids around or we dilate them. And so I'm sweeping a little bit under the rug here, but the basic idea is that if you average these operators out over some collection of shifted and translated dyadic grids, then you recover this continuous object. And there's also a similar result that's true for a more general Calder-Sigma operator, and this was proved in an Annals paper by Houdinin back in, I think, 2012 or somewhere around there. So the takeaway here is that the Haar shifts are good dyadic models for Calder-Sigma operators, and that's why we want to study them. There's another model of the Hilbert transform that's a dyadic model that is more recent, that was recently introduced by Pettermeikle and several co-authors. And this Haar shift, rather than mapping a Haar function to its children, kind of switches the siblings around. So it maps hi plus to hi minus and hi minus to minus hi plus. So h of hi is equal to the sine of I times hi sibling, precisely. And this operator, in some ways, it's a better model for the for the continuous Hilbert transform because it satisfies the anti-self adjoint property that if I look at h squared, I get minus the identity, right? And that's true of the classical Hilbert transform. It also mimics the Hilbert transform in that it maps cosine to sine and sine to negative cosine in some square wave sense. And the relevance for us is that this is the Haar shift whose commutator is known to characterize dyadic BMO. Now, this is all in the Lebesgue setting. I'll mention that if we move to the non-homogeneous setting, which is what we want to do, and we define H with Haar functions now that are orthonormal in L2 mu, you actually need to impose a weak dyadic regularity condition that's necessary and sufficient for this operator to be bounded on LP mu for P not equal to 2. So P equals 2 you get for free for P not equal to 2. If you don't have the dyadic doubling of the measure mu, you need to impose kind of this weak regularity condition. And we call this regularity condition sibling balanced. It's a somewhat technical condition to write down, so I'm not going to do that, but I just wanted to highlight that. Okay, and there are some results that we're also going to state in higher dimensions, so we can look at dyadic grids in Rn rather than just the real line. And we'll consider some locally finite Borel measure on Rn, and we'll also assume that that measure is strictly positive on each dyadic cube. And we can define these sort of probabilistic operators that are well known, such as the conditional expectation over a cube, where we average f on q multiplied by the characteristic function of q. And here the average, this bracket notation again just means integral average with respect to mu. And we can look at martingale difference operators, which are denoted by delta q and given as follows. So this difference of expectations of on the children minus the parent cube. And we're also going to use q hat to denote the dyadic parent of the cube q, just as in the one-dimensional case it denoted the parent dyadic interval. There's several BMO spaces that are going to play a role here. And now our BMO spaces are defined with respect to a Borel measure mu, which a priori has no doubling or other regularity assumptions. So we actually need to consider a few different variants of the classical BMO space. So the first one is what's known as this martingale BMO space. And the definition is almost the same as the classical definition of dyadic BMO, except rather than subtracting the average of B on Q, we subtract the average of B on its dyadic parent. And this turns out to be the space of BMO that's kind of right in terms of interpolation, also getting nice properties of BMO spaces, etc. And notice that there's an exponent of P here. I have an LP average rather than an L1 average. I'll say more about that in a moment. There's also this classical or Carlson packing BMO notion, which we denote by a lowercase b, BMOP. And for this one, we just subtract the average on Q rather than the average on the dyadic parent of Q. Okay? And when P equals 2, it turns out that this norm is equivalent to a reformulated Carlson packing condition where you sum up L2 norms of martingale differences on cubes that are all contained in some ancestor cube. Now, things are a lot more subtle if you don't assume that your underlying measure is doubling. So the martingale BMO space kind of has the nice classical properties that I was talking about. And in particular, these spaces are actually independent of P with equivalent norms. So if you're familiar with the John-Nuremberg inequality or the John-Nuremberg theorem, basically this is the John-Nuremberg theorem in this setting, is that it doesn't matter what exponent P I put here, I'm still going to get an equivalent norm. That's not true for the little BMO P spaces. When the measure is doubling, these spaces are equal to each other, but when mu is not doubling, these spaces are not equal in general, and in fact, in general, there's a strict containment that martingale BMO is strictly contained in this little BMOP space. All right. Um, there's some other dyadic operators that I want to briefly touch on. One is a paraproduct. Um, and basically, these operators come from taking the product of two functions, b and f, expanding them both out as a sum of martingale differences, and then grouping certain terms. So paraproduct really means like partial product. That's the way we should be thinking about it. And so the paraproduct with symbol b applied to f is the sum over dyadic cubes q of the expectation on q of f times the martingale difference on q of b. There's also the L2 adjoint of the paraproduct. If you compute the adjoint operator, this is what you get. There's sort of this diagonal operator delta B, which comes from the diagonal terms in the product expansion. And here we have delta QB, delta QF. That's why it's diagonal. And there's a couple of other operators that are relevant. This one here is equal to pi FB, so we kind of interchange the roles of B and F in the original paraproduct definition, right? So now I have an expectation on B and a martingale difference on F, as opposed to the reverse of that. And then there's also this dyadic operator, lambda B, that shows up as well when you look at certain terms. Okay. So one of our main theorems concerns sparse domination for such operators. And what's sparse domination? Well, it's emerged as a key tool in modern harmonic analysis in proving sharp weighted inequalities. And the general principle is that we dominate a complicated operator by some kind of simple positive dyadic averaging operator. And there are versions of this for both continuous and dyadic operators. So the definition of a dyadic sparse collection, I have some collection of dyadic cubes that's said to be eta sparse with a parameter eta in 0, 1. If for each Q in my collection there exists some measurable subset EQ that takes up at least some fixed amount of the measure of Q, and this collection of distinguished subsets is actually pairwise disjoint. So the
You have
original
2 more minutes.
intervals.
Yeah, you have a few more minutes.
Yeah. Okay. And so these distinguished subsets are pairwise disjoint, but the original intervals need not be. And this is actually equivalent to a Carlson packing condition. And so this is kind of a quick picture of a sparse collection. The orange intervals are the left halves of dyadic intervals as we shrink dyadically, starting with the interval 0, 1. And if I take the right half of each of those shrinking intervals, I get my distinguished pairwise disjoint subset. And basically, the reason why we like this is that we can dominate an operator by these dyadic sparse operators, which look very much like expectation operators, where the averages are taking over this sparse collection. Okay. And I know I have limited time, so I'm just going to say that a main application of sparse domination is that it can be used to prove weighted inequalities. So many operators, such as the Hardy-Littlewood maximal operator, Hilbert transform, Riesz transforms, more general Calderon-Zygmunt operators, in addition to commutators with BMO functions and paraproducts, are bounded on LPW if and only if the weight W belongs to what's known as this AP class. There's also a dyadic version of this class. And sparse domination is a streamlined tool to prove weighted inequalities for operators. And this situation is more complicated for non-homogeneous measures. There's an AP-like condition that still characterizes LPW bounds, but the condition is more technical to state and takes into account the non-homogeneous structure of the measure. And this is something that was sort of just recently developed. So our first result basically says that even in this non-homogeneous setting, a very general setting of a radon measure that's positive on dyadic cubes in Rn, and a martingale BMO function B for several of these dyadic operators, including the pair product, adjoint pair product, and this delta B operator, we do recover this sparse domination. So we can dominate such an operator by a very simple dyadic averaging operator over a sparse collection. And this immediately unlocks weighted estimates of the form the norm of T on LPW is controlled by a constant depending on P times the BMO norm times some sharp or what's expected to be sharp power of the dyadic AP characteristic. Um, and this is a new result that was not known in this generality before. There was a previous result due to Michael Lacey that it assumed more on the symbol of the pair product B, but now we can relax this to kind of the natural martingale BMO condition. And there's some applications of this. The first application is to look at the commutator with this model Hilbert transform, and it can be written in this paraproduct decomposition, which involves these dyadic operators that we actually have control over. And this allows us to unlock better weighted estimates for the commutator operator, assuming this weak dyadic regularity condition on mu, and also that it doesn't contain any atoms. And that's the main point of this corollary, is we can kind of apply this to get better weighted estimates for this commutator with an appropriate dyadic Hilbert transform. And the actual weight class is quite technical, but it's a strictly it's a weaker assumption than the prior result, which was known in the literature, and it's a muck and help type class. So it's similar to AP, but is a little bit more technical. We also characterize when the commutator is bounded on unweighted LP. And this was an interesting question because we had previously shown that the commutator cannot be used to characterize martingale BMO as in the classical case where the measure is Lebesgue measure or doubling. So in this non-homogeneous setting, if we assume just a kind of the minimum regularity requirement on the measure mu for things to make sense, which is what we call the sibling balance condition, we get a characterization for the bounds on LP of this commutator in terms of this. It's a somewhat technical condition. We call it commutator BMOP, denoted by a bracket BMOP. But the interesting thing that I want to point out here is that this space, in general, is strictly sandwiched in between martingale BMO and little BMO. So there's strict containments. Martingale BMO is strictly contained in this commutator characterizing class, which is in turn strictly contained in this little BMO space. And so that was really surprising and something that I think is kind of a novelty of our work in that we didn't necessarily expect to get the space that was sandwiched in between these two other well-known bounded mean oscillation spaces in the literature. Okay, so I know I'm out of time. Thank you very much for your attention.
Thank you. So we don't have enough time. Is there any quick question to the speaker? If not, let us thank the speaker again. Our next talk will start in 1 minute.